Do you know that feeling when you navigate a new code base, a sort of confusion mixed with curiosity? You go to your favorite AI agent and ask a painfully specific question that a normal human being would struggle to even parse. And after a while, the AI agent proceeds to generate a very thoughtful response. Somehow, against all odds, it identifies exactly the right file you were looking for, that needle in the haystack. Clearly, this is non-trivial because the exact words in my query don't even show up in the codebase at all. That's the challenge behind RAG, or Retrieval-Augmented Generation, the technique that gives an LM access to external documents so that its response can be substantiated. RAG is used in a lot of contexts. Agents like ChatGPT and Perplexity use it very transparently in order to build user trust in the LLM response. Other applications, like customer support bots, only use RAG behind the scenes without exposing internal documents to the customer. Right now, RAG is attracting a lot of drama. In a world where LLM context windows are ever increasing, the question is, do we need it in the first place? Can we just shove all the documents we have into the LLM and call it a day? And if we do need it, then what's the magic incantation that will make it work? It's really hard to answer these questions in the abstract. So instead, I've invited my friends from Continua AI to share part of their RAG pipeline. They've built a helpful AI assistant that joins your group conversation and contributes with meaningful and personalized suggestions. This is not a sponsored video. I've invited them because I really want to highlight real industry applications. So I'll start with a quick background on RAG, but if you're already a pro, feel free to skip directly to the guest chapter. Under the hood, RAG uses a retriever, a mechanism that, given a query and a set of documents, ranks them by relevance. The term Retrieval-Augmented Generation was coined in 2020, but the idea of matching questions to relevant documents goes back half a century. If we replace the LLM's prompt with a regular search query, we're back to the classic problem of information retrieval. For many decades, information retrieval relied on exact word counts. Given a set of documents, it would build a frequency matrix that counted how many times every vocabulary term occurred in every document. For a certain query Q and a document D, old methods would calculate a relevance score using carefully crafted formulas built directly on the term document matrix. This was the era of sparse retrieval. Sparse because the matrix has a lot of zeros. But relying on exact string match has serious limitations. Almost none of the natural language words in my query could be found in the relevant document. Deep neural networks propose a more robust alternative that matches based on semantics, not just characters. Text is projected to an n-dimensional vector space where these two seemingly different strings are neighbors. In this formulation, the relevance score of a document to a query becomes tied to their distance in the vector space. That's roughly where we are today, though embedding models keep evolving. In theory, dense retrieval should solve everything, but in practice, RAG pipelines are notoriously sensitive. There are just so many moving parts. There are two stages in the lifetime of a RAG pipeline: offline when pre-processing the documents, and online when serving the incoming queries. Offline during pre-processing, you face several decisions. First, there's chunking. How do we split long documents into chunks that the model can handle well? This is necessary because embeddings are a form of compression, and projecting of files with 50,000 lines of code into a couple thousand numeric values will lead to serious information loss. Then comes model choice. Out of the dozens of embedding models available, which one best fits your use case? For an incoming query, there are more decisions to be made. How many documents should we retrieve? Too few might risk missing the needle in the haystack. Too many might confuse the model, leading to context rot. And even after picking the top K most relevant documents, do you re-rank them with a more expensive but accurate model? And those are just the easy questions. There are a lot more subtle ones when you consider the specifics of your dataset, which might be multilingual or very heterogeneous, combining things like Slack conversations with design documents, with code files, which all require a different treatment. Unfortunately, there's no silver bullet. The best we can do is take inspiration from what others have done in the industry. So with that, I'll hand it over to Olga from Continua to share how they're applying RAG in the context of social AI.
Hi, I'm Olga. I'm a machine learning engineer at Continua, and today I'm going to be talking about how a method like HyDE plays into our actual product. So by now you know we're trying to build a social conversational AI, an agent that lives in your group chats and enhances the experience by being able to remind, recall, recommend, and entertain. So one of the things that makes an agent feel emotionally aware is a strong memory, something that makes the user feel seen and heard. Now, we don't want a user to have to prompt Continua in order to recall some tidbit of information. Rather, we want Continua to be able to automatically and seamlessly integrate that information. Retrieval-Augmented Generation is one of the tools we can use to do exactly that. Now, I'm going to level with you, it's actually quite hard to do. In the context of casual texting conversation, it's not always clear that retrieval is necessary. In fact, I would go as far to argue that most of the time it's not necessary at all. And I really want to make this distinction between necessary and nice to have. Generally, I think that when people think about retrieval, they think about it in the context of enterprise solutions. They think it's about retrieving documents, PDFs, or images that can be used to ground a response to a query. If I have a customer service bot, I need to be able to respond to users based on company policy. And in that case, there's this really clear notion of what is correct. In the context of casual texting conversations, it's not always so clear-cut. If I asked my agent, where should I go for dinner tonight? That's a search task. You can pull from search engines, Google Maps, and reviews to answer, and nobody would say that these answers are illogical or incorrect. You don't actually need to know my preferences to answer me. Obviously, if an agent can pull from previous conversations to personalize its response, the output will be much more satisfying to me. So here you see that the agent has retrieved previous conversations that mention that I love Thai food, I think supporting local businesses is great, and I really hated tabletop Thai. So these responses are a lot more personal to me. Now, there are many ways to build up this memory or preference store, but the one I'm focusing on in this presentation is, in fact, RAG. So in the context of our product, let's visualize how this will play out. All users have conversations with Continua, and as those conversations take place, they're vectorized and stored in some embedding space. For visualization, we'll pretend the space is three-dimensional, but in reality, these vectors are much, much larger with hundreds of dimensions, capturing a lot more nuance in the embedding. Here you see that we have a conversation where friends Max, Anne, and Sam are meeting up at the gym to play volleyball. Anne and Sam are running late, and Anne says, I hate driving in this city. Let's not make plans that involve driving anymore. Deal? And everybody agrees. And I would say that this tidbit of the conversation is very, very important. It tells Continua that it should really focus on local recommendations, and I would argue that it should be retrieved anytime Continua is providing suggestions for places to go. Great. So let's go ahead and embed this conversation in our embedding space. Because there's two separate semantic concepts being discussed in this conversation, let's say that it generates two embeddings, one that for the sake of visualization we'll label driving and the other as volleyball. Next, we have this conversation here where Max is discussing learning a new rollerblading trick and Continua is providing some tips and tricks. This might get embedded down here, close to the other sport-related embedding about volleyball. Then we have this conversation where Max, Anne, and Sam are discussing places to go for dinner, and Continua is suggesting a new Thai restaurant. Let's say that this ends up in the embedding space in this upper right-hand corner. Finally, we have a conversation about a potluck Max suggests bringing a shrimp cocktail, and Anne tells him, I literally can't have shellfish, so we can assume she's allergic. Obviously, that's going to be something that's super important for Continua to recall when making any sort of food-related recommendations. So let's say that it ends up in the embedding space, again in the upper right-hand corner, close to the dinner embedding, but slightly further away because instead of suggesting restaurants, we're talking about potlucks. Let's assume a bunch of time has gone by. We have plenty of conversations embedded, and now we're having a new conversation. This time I want to do retrieval. I'm going to embed this current conversation and then retrieve the k nearest neighbors to put in context before I generate a response. This conversation is really interesting because majority of it is about a rollerblading surprise party for Max. Continua makes some suggestions for the party, but the very last message in this conversation asks Continua, where should we go for dinner? The problem is that if we go ahead and embed this conversation as a whole, its embedding is going to be completely skewed towards the sports and rollerblading type embeddings, simply because the majority of the context is about that. So when we get the nearest neighbors, let's say k equals 3 here, none of them are going to be about dinner or potlucks or allergies, right? So you might suggest, okay, let's cut off the existing context and only embed the current message. But that'll end up, for sure, much closer to the dinner-related embeddings, but it won't be exactly next to them simply because the semantic density of this message will be much smaller than the other embeddings. Those other embeddings talked not just about the word dinner, it talked about restaurant recommendations and the types of food people are bringing to an event. And so this embedding won't be quite as close as we would hope. So when I get the k nearest neighbors, I'm still not capturing the other embeddings I would hope to. You might suggest rewriting this query, but that's not actually going to do anything to handle our semantic density issue. Mathematically, what's going wrong here is that we have a query document Q and another document D. We use the encoder or SumEncoder function to map both documents to an n-dimensional embedding space, and we define the similarity between Q and D as the inner product of our embeddings. The main issue is that Q and D have very different structures, and so our similarity is not as strong as we would hope or want it to be. You might ask why we don't use two separate embedding functions, one for the query document and one for the other documents. The reason is twofold. First and foremost, it's very hard. You then have two functions mapping to the same space, and you're hoping that they capture semantic meaning in an equal way. That's going to be very hard to measure without labeled training data. Second, realistically, as a startup, we don't always have the luxury of time to train our own model. We want to be able to move quickly and use things like embedding models off the shelf. We want to start simple and refine after the fact if and only if it's worth the investment. Therefore, we stick to using the same encoder function for both documents and focus only on augmenting our query document to match the same structure and format as our candidate documents. The question then becomes, how do we augment this query document? The answer is HyDE. So HyDE is a method that takes our input query document and uses a GPT-like model to generate potential candidate documents. These are completely fabricated conversations that match the structure of the existing documents in our vector store so that when we embed these candidates, they are much closer potentially to our target embeddings. So let's see how this would play out in the context of our existing conversational store. This is the first candidate that we've generated. It talks all about supporting local businesses and being able to walk to them. And so when we embed this one, let's say it ends up over here because it's talking about transportation, and so was our driving embedding. Next, we have this fabricated conversation. It talks about Anne saying she's severely allergic to avocado. Now, this didn't actually happen, but because I asked her a restaurant recommendation, I probably want to retrieve anything that mentions allergies. And so when we embed this candidate conversation, it does in fact end up near in space to our existing potluck/allergy mentioning embedding. Finally, we have this candidate conversation. It's just simply asking for dinner recommendations, and Continua is providing some sort of answer. And so this one's going to end up very, very close to our existing dinner embedding because the structure of these conversations is super similar. So now when we go to retrieve the documents from our embedding space, we're going to be able to retrieve 3 neighbors for every single candidate embedding. And you'll notice that with the candidates that we've come up with here, we're actually capturing the target embeddings we had hoped to. We're matching the one that's talking about dinner recommendations, the one that's talking about allergies, and even the one that's talking about our preference for local recommendations. This is great because the more relevant content we can show the model, the more personalized and satisfying we can make the response. However, this is an idealized scenario, and I would be remiss if I didn't acknowledge some of the added challenges that come from using HyDE. Number 1, latency. HyDE inevitably introduces an extra step to the retrieval pipeline, and every complication we add increases the time it takes for a user to get a response. Number 2, there are now many more retrieved candidates to sort through. The more diverse the content we retrieve, the more work we have to do in deciding what to actually use. We could choose to blindly show all retrieved content to the agent, but we would potentially pollute the context if the retrieved content is not truly relevant. If instead we rank retrieved content to filter it, this again adds latency. So this means we're constantly weighing the trade-off between quality and latency with every decision we make. The final challenge centers on tone matching. There should be some effort put in to ensure that the hypothetical generated documents actually match the tone of the user's real conversations, but I will say the best embedding models out there capture semantic as opposed to stylistic features, so I'm less concerned about this gotcha. There you have it. That's how we at Continua would integrate a method like HyDE into our product. Honestly, improving RAG performance is a real mix of both technical and creative innovation, and we're working every single day experimenting and innovating in order to improve our user experience.
Thanks to Olga and Continua for sharing part of their secret sauce. On my Patreon, you can find for free Olga's slide deck, as well as an interview with David Petru, the founder and CEO of Continua, who also happened to be my skip manager at Google. If you've enjoyed this format, let me know in the comments and I will bring in more case studies like this. Thanks for watching. See you next time.